Good morning, I am Seema from BSc Chemistry Honors second year. This video is usually for the visually impaired students, chapter Inorganic Chemistry, Chemistry of the Lanthanoid Elements. Lanthanoids are the elements present in page 6 of the periodic table with atomic number 57 to 71. Since the last electron in the atoms of these elements enters the 4f orbitals, therefore these elements constituent what is known as f-block elements. These elements are also named as inner transition elements. This is because these elements constituent a transition series within the third transition series. More precisely, the 5D transition elements. These elements are located in the first row of the two rows of elements kept at the base of the periodic table. The first element of the series is named lanthanum, and a group of the 14th elements following the lanthanum, which involves the gradual filling of the 4f orbitals, is called the lanthanides. In other words, elements starting from the cerium and ending with the lutetium are known as lanthanoids. The name lanthanoids was wrongly coined as the ending ide more correctly means a negative ion such as oxide or chloride ion. For a few years, IUPAC suggested a new name lanthanones instead of lanthanides to these elements. However, it was also disproved soon because the ending on is preferred for the non-metals, whereas the lanthanides are all typically metallic elements. IUPAC has finally approved these elements to be named as lanthanoids with the ending oid. These elements in the earlier years were called rare earth elements because of their occurrence in very small amount. However, nowadays the term rare earth elements is itself misleading because many of these elements have been found to be abundantly available. For example, cerium is as abundantly available as copper, whose deposits of these elements have been located in USA, USSR, Scandinavia, and India. Electronic structure and position of the lanthanoids in the periodic table. As already discussed, lanthanoids involve the gradual filling of 4f orbitals. The ground state electronic configuration of each lanthanoid is occupied by the outermost shell by the two 6s electrons. Since the energies of 6s, 5d and 4f are similar, the order of the filling the 4f orbitals may show some irregularities. It is found that at lanthanum, the incoming electron enters the 5d subshell and therefore it has the following electronic configuration. However, as we move onward after the lanthanum, the energy of the 4f subshell becomes distinctly lower than the 5d subshell. As a result, the next electron in the cerium enters the 4f subshell. The electronic configuration of the cerium is represented as cerium xenon 54 4f2 5d0 and 6s2. The filling of 4f subshell continues till one reaches deuterium, which has the electronic configurations xenon 54 4f14 5d0 6s2. F-block elements may be defined as those elements in which the last electron enters the anti-penultimate energy level, that is n-2 subshell. Since both the 6s and the 4f orbitals have been completely filled, the next electron has no choice but to go to the 5d orbitals. In lutetium, the electron enters the 5d orbitals and the electronic configuration is xenon 54 4f14 5d1 6s2. It is important to note that the electronic configuration of the penultimate shell is invariably S2p6 except for these elements lanthanum, gadolinium, lutetium. It is equally important to note that the 4f orbitals are unoccupied in the case of lanthanum. 4f orbitals are half filled in the case of gadolinium, and 4f orbitals are completely filled in the lutetium. General characteristics of the lanthanoid. The general electronic configuration of the lanthanoids may be represented as lanthanoids xenon 54 4f0 to 14 5d0 to 1 6s2. The ground state electronic configuration of the outer cells of the lanthanoid atoms are given in this table. Physical constants of the lanthanides. Some of the important physical constants of the lanthanoids are ionization energy. Lanthanides have low ionization energy. The first and the second ionization energy of the lanthanides increase in the general but will show little variation with the atomic number across the lanthanide series. The trend is less clear for the first ionization energy than for the sum of three ionizations. It is clear from that the dilations are observed only for europium, gadolinium, and deuterium or deuterium, which involves the half-filled and completely filled f orbitals. The first ionization energy of the lanthanides roughly correspond to the 550 kilojoules per mole, whereas the second ionization energy correspond to the 1150 kilojoule per mole. These values are comparable to the calcium, which has the first and second ionization energy values of the order of 590 kilojoule per mole and 1150 kilojoule per mole respectively. The next is the melting point. The melting point of any substance reflects the force of the attraction between the atoms, molecules, or the ions that compose the solid, as in section of the table 4.2 reveals that the lanthanides possess the high melting and boiling point. However, the melting and especially the boiling point of the lanthanides do not show any regular trend across the lanthanide series. The property of the lanthanides strongly suggests that 3 valence electrons per atom are involved in the metallic bond. The 4f electrons are not involved in the metallic bond, as these are located on the individual atoms and are well shielded from each other. The most clear cut anomalies in the lanthanoids are provided by the europium and deuterium, which behave much as would be expected of divalent metals, indicating less than 3 electrons per atom involved in the metallic bonding. These are also the two lanthanides which most rarely form the divalent ions in their compound. In addition, these two ions have half filled and completely filled for absorption. This explains the low melting point in case of europium and deuterium as compared to the values for the other lanthanoid elements. Density. The densities of the lanthanides do not display a regular trend across the lanthanide series. Both europium and deuterium have unusually low density. Heat of the fusion and heat vaporization. The amount of the heat required to convert a substance from a solid at its melting point to a liquid is called heat of fusion, whereas the amount of heat required to convert a substance from a liquid at its boiling point to a gas is called the heat of vaporization. In both the cases, the energy required is used to overcome the attractive forces. In case of lanthanides, the heat of fusion and the heat of vaporization do not show a regular trend across the lanthanide series. Electronegativity values. Pauling defined the electronegativity as the power of an atom in a molecule to attract the electron towards itself. The lanthanide shows the lower Pauling electronegativity values between the 1.0 to 1.15. These values are very close to those of the alkali metals 0.7 to 1.0 and alkaline earth metals 0.9 to 1.5. Since the electronegativity value of the lanthanides are almost same as that of S block elements, it is anticipated that lanthanoids form the ionic compounds. Oxidation state. The oxidation state of the third is shown by all these elements and in the most cases is the most stable oxidation state of the lanthanoids. Some of the lanthanides in addition plus 3 show plus 2 and plus 4 oxidation state as well. However, plus 2 and plus 4 oxidation state are always less stable than the plus 3 state. The reason for the unusual oxidation state of the plus 2 and plus 4 can be attributed to the extra stability associated with F0, F7 half filled and F14 completely filled electronic configuration. Example giving the various oxidation states are given below. Example of giving the various oxidation state are plus 3 oxidation state lanthanum, gadolinium and lutetium. Lanthanum, gadolinium and lutetium displays the plus 3 oxidation state. This is because after the loss of the 3 outermost electrons, these elements acquire the stable configuration of empty, half-filled and completely filled for absorption as shown. Plus 4 oxidation state. The most stable oxidation state of cerium is plus 4. This is because after the loss of the 4 electron, cerium acquires the outer electronic structure F0, D0, S0 which correspond to that of the noble gases. Cerium Z atomic number is 58. Cerium C4 positive X54 4F0 5D0 6S0. Similarly, terbium Z65 acquires the half filled F7 subcell configuration. Plus 2 oxidation state. The most stable oxidation state of europium is plus 2. This is because after the loss of the 2 electrons, europium acquires the outer electronic configuration of the half-filled F7 subcell configuration. Similarly, ytterbium acquires the outer electronic configuration of completely F14 subshell in the configurations. The outer electronic configuration of various lanthanides in different oxidation states are given in this table. These are the instances where some of the lanthanide displays the plus 2 and plus 4 oxidation state without acquiring either F0, F7 or F14 configuration. For example, samarium and thulium show plus 2 oxidation state with F6, F13 electron respectively, which are 1 electron short of the required half-filled F7 or completely filled F14 configuration. Similarly, praseodymium and neodymium show plus 4 oxidation state with F1 and F2 electronic configuration. The existence of such oxidation state which cannot be explained on the basis of F0, F7 or F14 configurations associated with the extraordinary stability might be explained on the basis of other factors such as the kinetic and thermodynamic factor. Magnetic properties. The magnetic properties in the chemical compound determine the presence of the paired or unpaired electron. If substance containing only spin paired electrons are placed in the magnetic field, these are weakly repelled by the field. This phenomena is called the diamagnetism. On the other hand, substances containing the one or more unpaired electrons when placed in the magnetic field are attracted by the magnetic field. This phenomena is called paramagnetism. It is important to note that the attraction of each unpaired electron is many times stronger than the repulsion of spin paired electrons in that atom. Most of the lanthanide ions, with the exception of the lanthanum 3 positive, Lu 3 positive, Ce 4 positive, and Be2 positive ions, are paramagnetic. The paramagnetism in the lanthanide ions arises because of the presence of unpaired electrons in their 4f subshell. The ions lanthanum, deuterium, cerium, and the erbium are diamagnetic because they have no unpaired electrons. The magnetic behavior of a substance is expressed in the terms of the magnetic moment. The larger the number of the unpaired electrons, the higher is the magnetic moment. The magnetic moment arises from the two types of the motion of the electrons. The spinning of the electrons on its own axis generates a magnetic moment called the spin magnetic moment. Orbital motion of the electrons around the nucleus also produces the magnetic moment called the orbital magnetic moment. The magnetic behavior in the case of the lanthanides arises due to the contribution of both spin magnetic moment as well as the orbital magnetic behavior. The behavior of the lanthanides is in contrast with the behavior of transition elements of d block elements, where the magnetic moment corresponds exclusively to the spin only values. In case of the transition elements, the d orbitals are not well shielded from the environment and interact strongly with the ligands surrounding the metal ion. Because of the electric field of the ligands, the orbital motion of the electron is restricted. That causes the orbital moment to decrease considerably. In other words, the orbital moment of the electrons in case of the transition elements can be neglected. On the other hand, in case of f block elements, the 4f subshells are well shielded from the surrounding and do not interact with the surrounding ligands. As a result, the orbital motion of the 4f orbitals is not restricted or quenched. Thus, the magnetic moment of the lanthanide ions arising due to the both electron spin and more orbital motion of the electron can be calculated from the expression mu is equal to under root 4s into s plus 1 plus l into l plus 1, where s is equal to total spin quantum number and L is the total magnetic quantum number. The magnetic moment theoretically and experiments for M3 positive lanthanoids ions are, for example, lanthanum 3 positive experimentally 0 and theoretically 0. Ion gadolinium 3 positive experiment 7.8 to 8.0 and theoretically is 7.90. This simple relationship works only for the lanthanides. Both lanthanum 3 positive and lutetium 3 positive have no unpaired electrons and consequently both have zero magnetic moment values. However, the magnetic properties of the lanthanides are different from those of the transition elements. In the lanthanides, the spin contribution and orbital contribution couple together to give a new quantum number J. The new quantum number J can have two types of values. J is equal to L minus N, where the orbital is less than the half full. J is equal to L plus S, where the orbital is more than the half full. Therefore, the magnetic moment values for the lanthanides in Bohr magnetum is given by mu is equal to G into J plus 1, where G is Landau splitting factor for the electron and is defined as Z is equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1, and the theoretically and experimental determined magnetic moment values of the tripositive lanthanide ion are given that. It is clear from that there is an excellent agreement between the theoretical and experimental values when the magnetic moment are calculated on the basis of spin and orbital contributions together. All the tripositive lanthanide ion expecting lanthanum 3 positive and lutetium 3 positive contain unpaired electrons and are therefore paramagnetic. A plot of the magnetic values of tripositive lanthanide ions reveals that the magnetic moment values increase first up to neodymium and then decrease up to samarium. It increases steadily again and reaches a maximum value for the dysprosium ion and then starts decreasing till it reaches zero value for the lutetium ion, which is diamagnetic. It is important to remark that the high values of the magnetic moment for Tb3 positive, di3 positive, and hafnium 3 positive clearly demonstrate the role of the orbital contribution towards the magnetic moment of the later lanthanoid. A distinct features of the curve is its unusual shape. The unusual shape of the curve arises because when the life F subshell is less than the half filled, the spin and orbital magnetic moment work in opposition. But when the F subshell is more than the half full, they work together, that is J into L plus S. The next is color and the spectral properties. The lanthanides in their element state are silvery white, while many lanthanide ions are distinctly colored, both in the solid state as well as in the aqueous solution. The color of the lanthanide ion depends primarily on the number of the unpaired electrons. The color of the lanthanide ion remains same even on changing the counter anion. Thus, the color of the lanthanide ion is characteristics of the cation. It has been found that the lanthanide ion containing the NF electron often have a similar color to those with 14 minus NF electrons. The color of the anthelides ion can be grouped symmetrically about the trivalent gadolinium ion. The color of the lanthanide ion is due to the primarily absorption of the light from the visible region of the spectrum that results in the electronic transition within the 4F level. This type of the transition is called FF transition. A unique feature of the spectra of tripositive lanthanide ions is that the absorption bands are sharp line like bands in the ultraviolet, visible or near infrared regions. This behavior is in contrast to the absorption bands of the DD type transition metals, which appears as broad absorption bands. The bands of the lanthanide ion are so sharp that they are used for characterizing lanthanides. The reason for very sharp absorption band is that the 4f orbitals are located deep inside the atom. Thus, they are effectively shielded from the environment factors such as nature and number of ligands which form the effectively shielded from environment factors such as nature and number of ligands which form the complex and from the vibrations of the ligand. A typical lanthanoid ion spectrum of the holmium. Thus, the color of the lanthanide ion does not change with different ligands. In other words, the absorption bands show the little dependence of the nature of ligand. It is important to mention here that this behavior is in contrast with the transition elements where dd transitions gives the absorption bands whose position changes from the ligand to ligand and width of the peak is greatly bounded because of the vibrations of the ligands. Vibration of the ligands changes the external field. However, the lanthanoids in the +2 and +4 oxidation state with the same number of electrons, isoelectronic ions, do not have the same color as observed in case of lanthanides in the +3 oxidation state. Some of the typical isoelectronic lanthanides in the +2 and +4 oxidation states after apart from ff transitions. Sometimes the color of the lanthanide ion can also be attributed to the fd transition. The ff absorption of the lanthanides ion have a very low intensity because of these transitions are not allowed. However, the FF absorption of lanthanides ion have the low intensity because these transitions are not the allowed. However, FT transitions are allowed. As a result, they show the very intense absorption bands. For example, cerium 3 positive and terbium 3 positive show the very intense absorption bands. Transitions due to the average bands are broadened in the contrast to narrow FF bands. In addition to FF and FD transitions, the color of the sum of the lanthanide ions can be due to the charge transfer. This transfer of the charge occurs from the lanthanide to the metals. This is more probably if the metal is in the high oxidation state or the ligands have the stronger reducing properties. Charge transfer usually produces the intense colors. For example, strong yellow color of the cerium 4 positive solutions arises due to the charge transfer rather than the FF transition. The blood red color of samarium 2 positive ion is also due to the charge transfer, ionic radii and the lanthanide contraction. Covalent and the ionic radii increases on moving down a group in the periodic table. This is due to the presence of the additional cells between the successive pairs. On the other hand, on moving from the left to right across a pair, the covalent and ionic radii decrease. This is attributed to the increased the effective nuclear charge, as a consequence of which the outermost electrons are attracted more and more. This results in the outermost electrons being pulled more and more closer. We also know that the shielding effect of the electrons decrease in the order S is greater than P, P is greater than D and F. The atomic and ionic radii of the lanthanoids are given there. A careful inspection reveals that as we move along the lanthanide series from the lanthanum to lutetium, there is a gradual decrease in the size of the atoms and ions. With the increase in the atomic number of it has been provided observed that in case of the tripositive lanthanide ions from the cerium 3 positive ions, the ionic radii decrease from the 1.03 angstrom to 0.86 angstrom. This shows that the overall decrease of 0.17 angstrom occurs in going from the cerium 3 positive to lutetium 3 positive ions. This is indeed a very small decrease in the comparison to the elements of the other groups and the pairs. The atomic radii of the elemental lanthanoids also decrease from the 1.83 angstrom. The total decrease of the atomic radii from the cerium to lutetium comes out to be the 0.10 angstrom. This small steady decrease in the atomic or ionic radii of the lanthanide elements with increase in the atomic number is called the lanthanide contraction. Cause of the lanthanide contraction. The shapes of the orbitals account for the relative atomic radii of the f block elements. The lanthanides involve the gradual filling of the 4f orbitals. The lobes of the f orbitals occupy the markedly different regions of the spaces and are therefore far apart from each other. Consequently, f orbital repel one another very weakly. Secondly, electron density in f orbital is low near the nucleus. As a result of being away from the nucleus, 4f orbital are not very effective at shielding effect other electrons from the nucleus. Thus, the increase in the atomic number and the nucleus charge, the effective nuclear charge expensed by the each 4f electrons increases. This increase in the inward pull of the 4f electrons and results in the reduction of the size of the atom of iron. This contraction in the size of the atom or ion by pulling the valence electron inward due to the high nuclear charge and the poor shielding effect of the f electron is the main cause of what it is called lanthanide contraction. Consequences of the lanthanide contraction. Some of the important consequences of the lanthanide contractions are given below. Steady decrease in the size of the lanthanide ion. As a result of lanthanide contraction, there is a gradual or steady decrease in the ionic radii of the lanthanide electronegativity. There is a slight increase in the electronegativity of the trivalent ions. Electrode potential values. There is a small but regular increase in the electrode potential values for the process. Resemblance of the second and the third transition series. The atomic radii of the elements of second transition series are typically greater than those in the first transition series. However, the radii of the third transition series elements are about the same size as that of second transition series. This similarly in the atomic radii is due to of the presence of f block near the beginning of the period 6th. There is a pronounced decrease in the atomic radii along the lanthanides. When the d block elements resume at the lutetium, the atomic radius has been fallen from 2.24 angstrom for barium to 1.72 angstrom for lanthanum. As a result of this, the atoms of all following elements are smaller than the expected. In brief, as a result of the lanthanide contraction, the chemistry of the second and third transition series resemble each other more than the elements of first and second transition series. Difficulty in the separation. Because of the very small change in the size of lanthanide ion in the lanthanide series, their chemical properties are alike. This causes the separation of the elements a difficult task. High density. The lanthanide contraction is responsible for the high density of the elements of third transition series. A block of the iridium, for example, contains as many atoms as block of the rhodium of the same volume, but each iridium atom is nearly twice as heavy as each rhodium atom. Therefore, the density of the iridium is nearly twice that of rhodium. Difference in the basicity. The size of the lanthanide ion decreases regularly with increase in the atomic number in the lanthanides. The decrease in the size of the cation tends to increase the covalent character according to Fajan's rule. As a result, the bonding of the smallest cation and hydroxide ion become mostly covalent. In other words, the basic strength of the hydroxide decrease. This explains clearly the LaO3 is the strongest while the lutetium hydroxide ion is the weakest base. Similarly to the hydroxides, there is also decrease in the basic strength of the oxides of the lanthanides with increase in the atomic number. This decrease in the basic strength of the oxides and the hydroxides of the lanthanides with increasing the atomic number is also reflected in several other related properties. For example, hydrolysis of the ions. Due to the decrease in the basic strength, there is a slight increase in the degree of hydrolysis in the solution from the lanthanum 3 positive to lutetium 3 positive. It means lanthanum 3 positive ions are less readily hydrolyzed than the lutetium 3 positive ion. Solubility of the salt. Hydroxides of the lanthanides precipitate with decreasing the pH values from the nitrides, of lanthanum 3 positive to lutetium 3 positive. It means lanthanum 3 positive ions are less readily hydrolyzed than the lutetium 3 positive ion. Solubility of the salts. Hydroxides of the lanthanides precipitate with the decreasing the pH values from the nitrides of lanthanum 3 positive to lutetium 3 positive ions at the 20 degrees Celsius. For example, lanthanide 3 positive ions precipitate at the pH 6.83, whereas gadolinium 3 positive precipitate at pH 6.83, while lutetium 3 positive precipitate at pH 6.30. Thermal decomposition of oxysalts. The stability of the trinitrates of lanthanides decreases with increase in the atomic number. Thus, the lanthanum nitrate, which is more basic, decomposes little where lutetium decomposes the readily. Complex formation tendency of the lanthanides. Compared to the transition metals, lanthanide ions do not readily form the complexes. It is primarily due to the larger size of the ions, which results in the smaller charge due to the ionic radius ratio. Lanthanides ions form the complexes preferably with the fluorine and oxygen donor ligands. They form the keto such as the acetyl acetone oximes, dimethyl ethylene diamine tetraacetate EDTA and hydroxycarboxylic acid such as the citric acid. Acetyl acetone complex of the tripositive lanthanide ion. The lanthanide elements are often 6 coordinated in the complexes. However, lighter coordinated numbers are also known in the some complexes. For example, 8 coordinated is found in the lanthanum, whereas acetyl acetone as well as in anionic species. The high charge density on the cerium 4 positive is accepted to form the stronger complexes than the tripositive ions. Cerium 4 positive has been found to form the dianionic complexes in the non-aqueous medium. This is an interesting complex in which the coordinated number of the cerium is 12. Nitrate ion behaves as a binded ligand. Organometallic compounds. Lanthanoids ion being highly electropositive do not form the complex with the pi bonding ligands. The inability to form the complex is also due to the non-availability of f orbitals for the bonding. However, lanthanides forms the two types of the compound. First is predominantly ionic cyclopentadienates, pi-bonded alkyl aryls. The cyclopentadienides can be prepared by the reaction of the anhydrous LnCl3 and NaC5H5 in a polar solvent like tetrahydrofuran in a appropriate molar ratio. Using this methodology, it is impossible to prepare the cyclopentadienes compounds of the type. In polar solvents, these complexes are highly solvated and monomeric in the nature. However, in the non-polar solvents, the tris compounds are insoluble while the bis compounds dimerize. The alkyl and aryl lanthanides can be prepared by the methodical reactions either in nth solutions. The triphenyl lanthanides are polymeric compounds. The first fully characterized compound was in which the lutetium atom is tetrahedrally coordinated to the 4 pi aryl groups. The methyl derivatives have recently been obtained. Occurrence of the lanthanoids. Lanthanoids were originally named as the rare earths because they were believed to be rare. However, the term rare earth is misleading as these are actually fairly common now. The word earth was used because most of these elements occur as the oxides, which in the early times meant earth. With the exception of promethium, which is radioactive, all the lanthanides occur naturally. Recent studies have been revealed that some of the lanthanides, namely cerium, lanthanum, and neodymium, occur in fairly abundant quantities. It has been found that the lanthanides with the odd atomic number are less abundant than the lanthanides with even atomic number. Cerium has been found to be almost as abundant as copper. All the lanthanides excepting cerium and promethium are more abundant than the iodine. The abundance of the lanthanide elements and the number of the naturally occurring isotopes. A number of the minerals containing the lanthanides are also known. Some of the important minerals are monazite. Monazite sand is the most important and widely spread mineral. It accounts for 78% of the mineral lanthanides. It predominantly contains phosphate of the lighter lanthanides with cerium, neodymium, and praseodymium together with smaller amount of the ytterbium and the heavier lanthanides along with the thorium phosphate. Monazite has been found to occur in Brazil, USSR, USA, southern India and Malaysia. Bastanicate. Bastanicate is a mixture of the fluorocarbonate with the formula M3CO3F, where M is Ce3 positive, lanthanum 3 positive, Nd3 positive, and the Pr3 positive. Bastanacate differs from monazite sands as it does not contain ytterbium and has the neighboring small amount of the thorium in it. Large deposition of the mineral bastanates found in Sweden and New Mexico. Ceriate. The mineral ceriate contains double silicates of cerium, lanthanum, praseodymium, niobium, and samarium along with the aluminium and the iron. Extraction of the lanthanides from the monazite. The mineral is crushed to obtain the fine powdered. It is digested with concentrated sulfuric acid till a paste of the lanthanide sulfate is obtained. The paste is separated by the centrifugation and treated with the cold water. When silica being insoluble is separated out, the solution containing the soluble sulfates is neutralized with the ammonium hydroxide. When thorium, zirconium, and titanium are precipitated as the respective phosphates, the resulting fiber is treated with the sodium sulfate. This treatment separates the lanthanide elements into two groups. The lighter lanthanides are precipitated out as double sulfates, while the heavier elements remain in the solution as simple the sulfates. The precipitated double sulfates of the heavier elements are treated with the concentrated solution of the sodium hydroxide, wherein these are converted into the mixture of the corresponding oxides and hydroxides. The mixture is subjected to the washing to remove the sodium sulfate forming during the course of the process and allowed to dry in air at 100 degrees Celsius. During this workup, cerium gets completely oxidized to the cerium 4th oxide, whereas the other lanthanides are converted to the sesquides. The resulting mixture of these oxides is treated with the dilute nitric acid HNO3. All the oxide except the CEO2 dissolve to form the corresponding nitrates. CEO2 being insoluble in the dilute HNO3 is separated out. This crud sample of CEO2 is dissolved in the concentrated HNO3. Addition of dilute sulfuric acid precipitate out cerium as basic nitrate of the formula CeOH NO3 3H2O, which is a red crystalline solid. The various steps involved in the separation of the cerium was outlined systematically in the flow sheet. After the successful separation of the cerium and the other anthenoids are separated into the individual elements by employing the different methods based primarily on the principle of various solubilities. Methods of separation into the individual components. The properties of the metal ions are governed by the size and the charge of the ions. Since all the lanthanide ions are nearly for the same size and invariable carry 3 positive charge, they have almost similar properties. As a result, the separation of the lanthanides from one another is extremely difficult. A number of the methods have been recently been developed based upon the repeated fractional crystallization, fractional precipitation, ion exchange methods, etc. for the separation of lanthanides. The conventional method of the separation takes advantage of the slight differences in basic properties, solubilities or stability However, recently ion exchange method has been found to be the simplest. Some of the methods are discussed below. Precipitation. With a small amount of the precipitating agents, a substance with the lowest solubility is precipitated out first. Suppose hydroxyl ions OH are added to a solution containing a mixture of the lanthanide nitrates. The weakest base, lutetium hydroxide ion, has the lowest solubility product is precipitated first, and the strongest base, lanthanum hydroxide, which has the highest solubility product, is precipitated last. The process, when repeated several times, helps in the complete separation of the lanthanides. Fractional crystallization. Simple salts of the lanthanides such as the nitrate, oxalate, sulfate, perchlorates together with the double salts such as the 2Ln nitrate to 3Mg nitrate 24H2O form well-defined crystals. The solubility of these salts decrease from lanthanum to lutetium. As a result, salts at the end of the series, example lutetium salts which have the low solubility, will crystalline out similarly. Salts at the starts of the series with while are most soluble will the crystalline out in the end. The process requires the repeated crystallizations to get the good separation. This is a laborious method of separation and it is not perfected these days. Solvent extraction. This method of separation is based upon the fact that the solubility of the lanthanide nitrates in the aqueous and organic solvents like tributyl phosphate is different. In the solvent extraction process, a dilute aqueous nitric acid solution of the lanthanides is extracted by means of the counter flowing solutions of the tributyl phosphate in the kerosene. Thus, in the extraction from the aqueous nitric acid solutions by tributyl phosphate, the equilibrium is established. The extent of the extraction increases with the decrease in the ionic radius. In other words, the cation of the elements with the higher atomic number are extracted the first. Using this method, a high degree of the separation is achieved. Complex formation. Complexing agents like ethylene diamine tetraacetate are well known to form the complexes with the lanthanides. The stability of these complexes increases with decrease the size of the lanthanide ion. Thus, lutetium ion complex of EDTA is the most stable of all the complex of the lanthanides with the EDTA. If some acid is added to the solution of this complex with EDTA, the least stable EDTA complex will some acid is added to the solution of these complexes with the ETTA. The least stable EDTA complex will dissociate and release of the lanthanide ion. Addition of the oxalic acid will immediately precipitate out the free lanthanide ion, preferably at the left hand side to series. Oxalate of the lanthanides are insoluble in the water. However, addition of the oxalate ions to the EDTA complex lanthanide ion will not precipitate the lanthanide ions as they are already complexed with the EDTA. Change in the oxidation state. Most of the lanthanides exhibit an oxidation state of the 3 in its compounds, whereas a few lanthanides show the oxidation state +2 and +4 in its compound. As a result, lanthanides with the +3 oxidation state have properties together different from the lanthanoids with +2 and +4 oxidation state. The difference in the properties in the different oxidation state is extremely useful in the separation of lanthanides. Cerium can be separated from the mixture of the lanthanides easily because it is the only the lanthanoid which has +4 oxidation state in the aqueous solution. Thus, if the alkaline KMnO4 is added to the mixture of lanthanides, it is only the cerium which will oxidize to the +4 oxidation state. On account of high charge, cerium 4 positive is the smallest and less basic than the cerium 3 positive ion. It can be separated by precipitating it is cerium hydroxide by the addition of the sodium hydroxide, leaving behind the other trivalent ions in the solution. Similarly, europium can be separated from the rest of the lanthanide because europium is the only the lanthanide which is stable in the +2 oxidation state. Addition of the zinc amalgam, a reducing agent, to the mixture of lanthanide ion only reduce europium 3 positive, europium 2 positive, leaving the behind lanthanoids in the +3 oxidation state. If H2SO4 is added at this stage, europium 2 positive ion is only precipitated at europium sulfate. Europium sulfate, while the sulfate of all the lanthanide ion remain in the solution as the lanthanum sulfate. It is important to mention that samarium and eubium can also be separated by the reducing with the zinc amalgam. However, these get oxidized slowly by the water, unlike the European ion exchange method. Ion exchange method is one of the most convenient and efficient method for the separation and purification of the lanthanoid. In this method, a solution of the lanthanide ion is passed through the column of synthetic ion exchange resin which contains the functional group. Lanthanide ions, when come in contact with the resin containing the acidic functional group, undergo the proton exchange. In the process, lanthanide ions are bonded to the regions as the H positive ions produced are washed through the column. The bonding of the lanthanide ion to the resin depend on the size of the lanthanide ion. Since the lanthanide ion are present in the aqueous solution, these are heavily hydrated. The smaller the lanthanide ion, most heavily hydrated is it. Thus, lutetium ion, which is the smallest in size, is the most heavily hydrated ion. It means that the size of the hydrated lutetium ion is maximum. It means that the smaller the size, hydrated lanthanide ions bind strongly with the resins, and large size lanthanide ion binds loosely with the resin. The bonded metal ions are eluted, that is washed off the column by a complexing agents. The commonly used complexing agent is a buffered solution of citric acid. As already discussed, hydrated lutetium ion, being the largest size ion, will bind less firmly to the resin. It therefore will be evaluated first. On the other hand, hydrated lanthanum ion, being the smallest size hydrated ion, will bind strongly to the resin. Therefore, it will be evaluated in the last of all. Using ion exchange methods, it is possible to separate all the trivalent lanthanide ion based upon the strength of which these are bonded with the resin, which in turn depends upon the size of the hydrated lanthanide ion. In brief, the heavier lanthanide elements will be eluted or washed down the column first, followed by the less heavier elements, and finally by the highest lanthanide elements. Lutetium curve of the lanthanide elements from an ion exchange resin column. Production of the lanthanide elements. We have discussed in the preceding sections a number of the methods for the separation of the closely related lanthanides. In this section, we shall illustrate the methods for the production of the elements. Electrolysis of the fused elements. Chlorides. A mix of the lanthanide chloride is fused with the NaCl or calcium chloride and electrolyzed in a graphite line steel shell, serves as the cathode and graphite rod as the anode. Reaction of the anhydrous chloride with the sodium. Lighter lanthanides such as lanthanum, cerium, and gadolinium are prepared by the reduction of the corresponding trichlorides with the element sodium. Reduction of the anhydrous trifluorides with calcium or magnesium. Heavier lanthanoids are produced by the reduction of anhydrous trifluorides with elemental calcium. Anhydrous trifluorides are prepared because these are non-hygroscopic and less volatile than the trichlorides, and secondly the resulting CF2 produced is stable. Compounds of the lanthanoids. All the lanthanides are soft and silvery white metals. They are highly electropositive and reactive. They heavier elements are less electric than the lighter lanthanides because they form a protective layer of oxides on their surface. Most of the lanthanides form the compounds in the +3 oxidation state. However, some compounds of lanthanides in the +2 and +4 oxidation state are also well known. Let us discuss this. Lanthanoids oxides. All the lanthanum metals tarnish readily in the air. These burn in the oxygen, forming the corresponding. The oxides can also be prepared conveniently either by heating the carbonates or by decomposing the corresponding nitrate. Lanthanide oxides are known to absorb the water and carbon dioxide from the air to form the hydroxides and with the carbonates respectively. As a result, these are basic in the nature. The basic character of the oxide decrease with increase in the atomic number of the lanthanide. This is due to the lanthanide contraction wherein the size of the lanthanide decrease from lanthanum to lanthanum. Lanthanide oxides. The lanthanide hydroxides are reactive metals. These react slowly with cold water but more rapidly on boiling with the hot liberation of hydrogen to form the corresponding hydroxide. The hydroxide can also be prepared by adding dilute hydroxide solution to a containing Ln3 positive ion. Lanthanide halides, lanthanide trifluorides are obtained by the reaction of HF in the solution containing the lanthanide ion. Lanthanide fluorides are more important because of their insolubility. However, fluorides of heavier lanthanides are slightly soluble in the excess HF. Anhydrous lanthanides chlorides are prepared by heating the metal in atmospheric of the chlorine. Hydrated chlorides can be conventionally prepared by heating the oxides with the appropriate ammonium halide. The chlorides are non volatile delicate solids. They are soluble in water with the crystalline 6-7 molecules of water of crystallization. The anhydrous lanthanide trichlorides cannot be prepared by the simply heating the hydrated lanthanide trichloride. In fact, of heating the hydrated trichlorides are converted to oxychlorides. The tribromides are more susceptible to hydrolysis and generally contaminated with the oxyhalides. Lanthanide nitrates. A high temperature of the lanthanide react with the nitrogen to give the nitride the formula Ln, and it gets hydrolyzed by the water to give the corresponding hydroxide with the liberation of ammonia. Oxosalts of the lanthanide. A large number of the oxosalts of the lanthanum are known. These include the nitrates, carbonates, sulfates, oxalates, phosphate, and perchlorates. They are generally prepared by the dissolving the lanthanide oxides. The resulting solution are cooled when crystal of hydrated oxosalts are obtained. Double salt of the lanthanides. It is important to note that lanthanide sulfates are known to form the double salt with the ammonia, and alkali metal sulfates forms the composition. The double salts in the case of alum are generally associated with the 24 water molecules of the crystalline. Thank you.